The Theoretical Minimum by Leonard Susskind, Lecture 2, Motion. Lenny complained, "George, this jumpy, stroboscic stuff makes me nervous. Is time really so bumpy? I wish things would go a little more smoothly." George thought for a moment, wiping the blackboard. "Okay, Lenny, today let's study systems that do change smoothly." Mathematical Interlude, Differential Calculus. In this book, we will mostly be dealing with how various quantities change with time. Most of classical mechanics deals with things that change smoothly. Continuously is the mathematical term, as time changes continuously. Dynamical laws that update a state will have to involve such conscious changes of time, unlike the stroboscic changes of the first lecture. Thus, we will be interested in functions of the independent variable t. To cope mathematically with continuous changes, we use the mathematics of calculus. Calculus is about limits. So let's get the idea in place. Suppose we have a sequence of numbers L1, L2, L3, and so on that get closer and closer to some value, capital L. Here is an example: 0.9, 0.99, 0.999, 0.9999, and so on. The limit of this sequence is 1. None of the entries is equal to 1, but they get closer and closer to that value. To indicate this, we write limit I to infinity, Li equals capital L. In other words, capital L is the limit of small li as I goes to infinity. We can apply the same idea to functions. Suppose we have a function ft and we want to describe how it varies as t gets closer and closer to some value, say a. If ft gets arbitrarily close to capital L as t tends to a, then we say that the limit of ft as t approaches a is the number capital L. Symbolically, the limit of when t approaches small a, ft equals capital L. Let ft be a function of the variable t. As t varies, so will ft. Differential calculus deals with the rate of change of such functions. The idea is to start with function ft at some instant and then to change the time by a little bit and see how much ft changes. The rate of change is defined as the ratio of the change in f to the change in t. We denote the change in a quantity with the uppercase Greek letter delta. Let the change in t be called delta t. This is not delta cross t, this is a change in t. Over the interval delta t, function f changes from ft to ft plus delta t. This change in f, denoted delta f, is given by delta f equals function of t plus delta t minus ft. To define the rate of change precisely at time t, we must let delta t shrink to 0. Of course, when we do that, delta f also shrinks to 0, but if we divide delta f by delta t, the ratio will tend to a limit. That limit is the derivative of ft with respect to t. d of t by dt equals limit delta f by delta t, that is limit delta t tends to 0, and the difference of ft plus delta t minus ft divided by delta t, equation 1. A rigorous mathematician might frown on the idea that d of t by dt is the ratio of two differentials, but you will rarely make a mistake this way. Let's calculate a few derivatives. Begin with functions defined by powers of t. In particular, let's illustrate the method by calculating the derivative of ft equals t squared. We apply equation 1 and begin by defining ft plus delta t. ft plus delta t equals t plus delta t whole square. We can calculate t plus delta t whole square by direct multiplication, or we can use the binomial theorem. Either way, ft plus delta t is t square plus 2t plus delta t square. We now subtract ft. ft plus delta t minus ft eventually gives us 2t delta t plus delta t square. The next step is to divide by delta t, and eventually you get the expression 2t plus delta t. Now it's easy to take the limits of delta t to 0. The first term does not depend on delta t and survives, but the second term tends to 0 and just disappears. This is something to keep in mind. Terms of higher order delta t can be ignored when you calculate derivatives. Thus, the limit of delta t tending to 0, like f delta t plus t minus ft by delta t, equals 2t. So the derivative of t square is 2t. Next, let us consider a general power, ft equals t power n. To calculate its derivative, we have to calculate ft plus delta t equals t plus delta t whole power n. Here, high school algebra comes in handy. The result is given by the binomial theorem. Given two numbers a and b, we would like to calculate a plus b power n. The binomial theorem gives a plus b power n, expansion of the binomial theorem, a power n plus n a power n minus 1 b, blah blah blah. How long does the expression go on? If n is an integer, it eventually terminates after n plus 1 terms. But the binomial theorem is more general than that. In fact, n can be any real or complex number. If n is not an integer, however, the expression never terminates. It is an infinite series. Happily, for our purposes, only the first two terms are important. To calculate t plus delta t power n, all we have to do is plug in a equals t and b equals delta t to get f t plus delta t equals t plus delta t whole power n, and then the expansion in binomial way, tn plus n tn minus 1 times delta t, and so on. All the terms represented by the dots shrink to 0 in the limit, so we ignore them. Now subtract ft or t power n from that. That gives us our delta f. Delta f equals ft plus delta t minus ft, and then t power n plus t power n minus 1 delta t plus ... Now finally divide it by delta t, and eventually you get nt power n minus 1 plus nn minus 1 power over 2 tn minus 2 delta t. Now let delta t tend to 0. The derivative is then dt power n by dt equals n t n minus 1. One important point is that this relation holds even if n is not an integer. N can be any real or complex number. Here are special cases of derivatives. If n equals 0, then ft is just the number 1. The derivative is 0. This is the case for any function that doesn't change. If n equals 1, then ft equals t, and the derivative is 1. This is always true when you take the derivative of something with respect to itself. Here are some derivatives of powers. Derivative of t square, t cube, t power 4, t power n. For future reference, here are some other derivatives. Derivative of sine is cos, derivative of cos is minus sine, derivative of e power t, that is exponential to the power t, is et, and the derivative of logarithm t is 1 by t. One comment about the third formula in equation 2, the derivative of exponential power t. The meaning of exponential power t is pretty clear if t is an integer. For example, e cube is e times e times e. Its meaning for non-integers is not obvious. Basically, exponential power t is defined by the property that its derivative is equal to itself. So the third formula is really a definition. There are a few useful rules to remember about derivatives. You can prove them all if you want a challenging exercise. The first is the fact that the derivative of a constant is always 0. This makes sense. The derivative is the rate of change, and a constant never changes. So dc by dt equals 0. The derivative of a constant times a function is the constant times the derivative of the function. As in, d derivative of cf by dt equals c df by dt, where c is the constant. Suppose we have two functions, ft and gt. Their sum is also a function, and its derivative is given by df plus g by dt gives us derivative of f and derivative of g sum. This is called the sum rule. The product of two functions is another function, and its derivative is dfg by dt gives us ft and the derivative of g plus gt and the derivative of f. Not surprisingly, this is called the product rule. Next, suppose that gt is a function of t and fg is a function of g. This makes f an implicit function of t. If you want to know what f is for some t, you first compute gt. Then, knowing g, you compute fg. It's easy to calculate the t derivative of f. df by dt equals df by dz times dz by dt. This is called the chain rule. This would obviously be true if the derivatives were really ratios. In that case, the dz's would cancel in the numerator and denominator. In fact, this is one of those cases where the naive answer is correct. The important thing to remember about using the chain rule is that you invent an intermediate function gt to simplify ft, making it fg. For example, if ft equals ln t power 3 and we have to find df by dt, then the t power 3 inside the logarithm might be a problem. Therefore, we invent the intermediate function g equals t cube. So we have fg equals logarithm of g. We can apply the chain rule. Df by dt equals df by dg times dg by dt. We can use our differentiation formulas to note that df by dz is 1 by g and dg by dt is 3t square. So df by dt becomes 3t square by g. We can substitute g equals t cube to get df by dt equals 3t square by t cube, which is equals 3 by t. This is how to use the chain rule. Using the chain rules, you can calculate a lot of derivatives. That's basically all there is to differential calculus. Exercise 1. Calculate the derivatives of each of these functions. Exercise 2. The derivative of a derivative is called the second derivative and is written d square ft by dt square. Take the second derivative of each of the functions listed above. Exercise number 3. Use the chain rule to find the derivatives of each of the following functions. Exercise 4. Prove the sum rule. Fairly easy. The product rule. Easy if you know the trick. And the chain rule. Fairly easy. Exercise 5. Prove each of the formulas in equation 2. Hint: look up trigonometric identities and limit properties in the reference book. Particle motion. The concept of a point particle is an idealization. No object is so small that it is a point, not even an electron. But in many situations, we can ignore the extended structure of objects and treat them as points. For example, the planet Earth is obviously not a point, but in calculating its orbit around the Sun, we can ignore the size of Earth to a high degree of accuracy. The position of a particle is specified by giving a value for each of the 3 spatial coordinates, and the motion of the particle is defined by its position at every time. Mathematically, we can specify a position by giving the 3 spatial coordinates as functions of t: xt, yt, and zt. The position can also be thought of as a vector rt, whose components are x, y, z at time t. The path of the particle, its trajectory, is specified by vector rt. The job of classical mechanics is to figure out vector rt from the initial condition and some dynamical law. Next to its position, the most important thing about a particle is its velocity. Velocity is also a vector. To define it, we need some calculus. Here is how we do it. Consider the displacement of a particle between time t and a little bit later at time t plus delta t. During that time interval, the particle moves from xt, yt, zt to xt plus delta t, yt plus delta t, and zt plus delta t, or in vector notation, from vector rt to vector rt plus t. The displacement is defined as displacement x equals xt plus delta t minus xt, and correspondingly for y and z. Therefore, displacement delta vector r equals vector r at t plus delta t minus vector r at t. The displacement is the small distance that the particle moves in the small time delta t. To get the velocity, we divide the displacement by delta t and take that limit as delta t shrinks to 0. For example, the velocity vx equals the limit when delta t tends to 0, the ratio delta x by delta t. This, of course, is the definition of the derivative of x with respect to t. Therefore, vx is equal to dx by dt, also written as x dot. Vy is equal to dy by dt, also written as y dot. And vz is equal to dz, derivative of z with respect to t, also represented by z dot. Placing a dot over a quantity is standard shorthand for taking the time derivative. This convention can be used to denote the time derivative of anything, not just the position of a particle. For example, if capital T stands for the temperature of a tub of hot water, then capital T dot will represent the rate of change of temperature with time. It will be used over and over, so get familiar with it. It gets tiresome to keep writing x, y, z, so we will often condense the notation. The 3 coordinates x, y, z are collectively denoted by xi and the velocity by vi. Vi equals the time derivative of xi, which is xi dot. where I takes the values of x, y, and z, or in vector notation, vector v equals the time derivative of vector r with respect to t, which equals vector r dot. The velocity vector has a magnitude modulus of vector v. Therefore, the square of the modulus of vector v equals vx square plus vy square plus vz square. This represents how fast the particle is moving without regard to the direction. The magnitude modulus vector v is called speed. Acceleration is the quantity that tells you how the velocity is changing. If an object is moving with a constant velocity vector, it experiences no acceleration. A constant velocity vector implies not only a constant speed, but also a constant direction. You feel acceleration only when your velocity vector changes, either in magnitude or direction. In fact, acceleration is the time derivative of velocity. AI equals dvi by dt, which is vi dot. Or in vector notation, acceleration vector A equals vector v dot. Because vi is the time derivative of xi and ai is the time derivative of vi, it follows that acceleration is the second time derivative of xi. So correspondingly, ai equals the d squared x by dt square, which is xi dot dot, representing double derivative, where the double dot notation means the second time derivative. Examples of motion. Suppose a particle starts to move at the time t equals 0 according to the equations xt equals 0, yt equals 0, and zt equals z at 0 plus v at 0 times t minus half gt square. The particle evidently has no motion in x and y directions but moves along the z axis. The constants z0 and v0 represent the initial values of the position and velocity along the z direction at time t equals 0. We also consider g to be a constant. Let's calculate the velocity by differentiating with respect to time. vxt equals 0, vyt equals 0, vzt equals v0 minus gt. The x and y components of velocity are 0 at all times. The z component of velocity starts out at t equals 0 being equal to v0. In other words, v0 is the initial condition for velocity. As time progresses, the minus gt term becomes non-zero. Eventually, it will overtake the initial value of the velocity and the particle will be found moving along in the negative z direction. Now let's calculate the acceleration by differentiating with respect to time again. axt equals 0, ayt equals 0, and azt is minus z. The acceleration along the z-axis is constant and negative. If the z-axis were to represent the altitude, the particle would accelerate downward in just the way a falling object would. Next, let's consider an oscillating particle that moves back and forth along the x-axis. Because there is no motion in the other two directions, we will ignore them. A simple oscillatory motion uses trigonometric functions. xt equals sine wt, where the lowercase Greek letter omega is a constant. The larger omega, the more rapid the oscillation. This kind of motion is called simple harmonic motion. See figure 1. Let's compute the velocity and the acceleration. To do so, we need to differentiate xt with respect to time. Here is the result of the first time derivative. Vx is equal to the derivative of sine omega t by t dt. We have the sign of a product. We can relabel this product as b equals omega t. That is, Vx is equal to d sine b by dt. Using the chain rule, Vx is equal to d by dv sine b, db by t, or Vx is equal to cos b, the derivative of wt by dt, eventually gives us Vx is equal to omega cos omega t. We get acceleration by similar means. Ax is equal to minus omega square sine omega t. Notice some interesting things. Whenever the position x is at its maximum or minimum, the velocity is 0. The opposite is also true. When the position is at x equals 0, then velocity is either maximum or minimum. We say that position and velocity are 90 degrees out of phase. You can see in figure 2 representing xt and figure 3 representing vt. Figure 2 representing position, figure 3 representing velocity. The position and acceleration are also related, both being proportional to sine omega t. Notice the minus sign in the acceleration. That minus sign says that whenever x is positive, negative, the acceleration is negative, positive. In other words, whatever the particle is, it is being accelerated back toward the origin. In technical terms, the position and acceleration are 180 degrees out of phase. Exercise 6. How long does it take for the oscillating particle to go through one full cycle of motion? Next, let's consider a particle moving with uniform circular motion about the origin. This means that it is moving in a circle at a constant speed. For this purpose, we can ignore the z-axis and think of the motion in the xy plane. To describe it, we must have two functions, xt and yt. To be specific, we will choose the particle to move in the counterclockwise direction. Let the radius of the orbit be r. It is helpful to visualize the motion by projecting it onto the two axes. As the particle revolves around the origin, x oscillates between x equals to minus r and x equals r. The same is true of the y coordinate. But the two coordinates are 90 degrees out of phase, and when x is maximum, y is 0, and vice versa. The most general, counterclockwise uniform circular motion about the origin has the mathematical form xt is equal to capital R cos omega t and yt equals capital R sin omega t. Here the parameter omega is called the angular frequency. It is defined as the number of radians that the angle advances in unit time. It also has to do with how long it takes to go one full revolution, the period of motion, the same as we found in exercise 6. Capital T equals 2 pi by omega. Now it is easy to calculate the components of velocity and acceleration by differentiation. Vx equals minus r omega sin omega t, Vy equals r omega cos omega t, Ax equals minus r omega square cos omega t, and Ay equals minus r omega square sin omega t. This shows an interesting property of circular motion that Newton used in analyzing the motion of the moon. The acceleration of a circular orbit is parallel to the position vector, but it is oppositely directed. In other words, the acceleration vector points radially inward toward the origin. Exercise 7. Show that the position and velocity vectors are orthogonal. Exercise 8. Calculate the velocity, speed, and acceleration for each of the following position vectors. If you have a graphing software, plot each position vector, each velocity vector, and each acceleration vector. Interlude 2. Integral Calculus. George, I really like doing things backward. Can we do differentiation backward? Sure we can, Lenny. It's called integration. Integral calculus. Differential calculus has to do with rates of change. Integral calculus has to do with sums of many tiny incremental quantities. It's not immediately obvious that these have anything to do with each other, but they do. We begin with the graph of a function ft as in figure 1. Figure 1, the behavior of ft. The central problem of integral calculus is to calculate the area under the curve defined by ft. To make the problem well defined, we consider the function between two values that we call limits of integration, t equals a and t equals b. The area we want to calculate is the area of the shaded region in figure 2. Figure 2, the limits of integration. In order to do this, we break the region into very thin rectangles and add their areas. See figure 3. Figure 3, an illustration of integration. Of course, this involves an approximation, but it becomes accurate if we let the width of rectangles tend to 0. In order to carry out this procedure, we first divide the interval between t equals a and t equals b into a number, n, of subintervals, each of width delta t. Consider the rectangle located at a specific value of t. The width is delta t, and the height is the local value of ft. It follows that the area of a single rectangle, delta A, is delta A equals ft times delta t. Now we add up all the areas of the individual rectangles to get an approximation to the area that we are seeking. The approximate answer is capital A equals summation of I ft times delta t, where the uppercase letter sigma indicates a sum of successive values defined by I. So if n equals 3, then A equals sigma I to 3 ft delta t, which when expanded gives us ft1 delta t plus ft2 delta t plus ft3 delta t. Here ti is the position of the ith rectangle along the t-axis. To get the exact answer, we take the limit in which delta t shrinks to 0 and the number of rectangles increases to infinity. That defines the definite integral of ft between the limits t equals a and t equals b. We write this as capital A equals integration from a to b ft dt. That gives us limit delta t to 0 summation I ft delta t. The integral sign, called summa, replaces the summation sign, and as in differential calculus, delta t is replaced by dt. The function ft is called the integrand. Let's make a notational change and call one of the limits of integration capital T. In particular, replace b by capital T and consider the integral. Capital Ft equals summa from small a to t ft dt. Thus, a given function ft defines a second function capital F capital T. We could also let a vary, but we won't. The function ft is called the indefinite integral of ft. It is indefinite because instead of integrating from a fixed value to a fixed value, we integrate to a variable. We usually write such an integral without limits of integration. For example, capital Ft equals summa of ft dt. The fundamental theorem of calculus is one of the simplest and most beautiful results in mathematics. It asserts a deep connection between integrals and derivatives. What it says is that if the function capital Ft equals summa of small f t dt, then function ft equals the time derivative of d of t. To see this, consider a small incremental change in t from t to t plus delta t. Then we have a new integral. Ft plus delta t equals summa a to t plus delta t ft dt. In other words, we have added one more rectangle of width delta t at t is equal to capital T to the area shaded in figure 3. In fact, the difference ft plus delta t minus ft is just the area of that extra rectangle, which happens to be the function at capital T times delta t. So ft plus delta t minus ft equals ft times delta t. Dividing it by delta t, we get this. Thus obtain the fundamental theorem connecting capital function f with the small f when we take the limit where delta t tends to 0. And when we take the limit where delta t tends to 0, the derivative of capital function f with respect to time gives us small f t. We can simplify the notation by ignoring the difference between small t and big T. That gives us the time derivative of capital F function equals ft. In other words, the processes of integration and differentiation are reciprocal. The derivative of the integral is the original integrand. Can we completely determine ft knowing that its derivative is small ft? Almost, but not quite. The problem is that adding a constant to capital Ft does not change its derivative. Given ft, its indefinite integral is ambiguous, but only up to adding a constant. To see how the fundamental theorem is used, let's work out some indefinite integrals. Let's find the integral of a power ft equals t power n. Consider capital Ft equals the summa of ft dt. It follows that Tn equals df by dt. All we need to do is find a function f whose derivative is t power n, and that is easy. In the last chapter, we found that for any m, the derivative of t power m with respect to time is m t power m minus 1. If we substitute m by n plus 1, this becomes derivative of t power n plus 1 equals n plus 1 times t power n. Then dividing by n plus 1, we eventually get t power n. Thus, we find that t power n is the derivative of t power n plus 1 by n plus 1. To substitute the relevant values, we get the function capital Ft equals the summa of t power n dt equals t power n plus 1 by n plus 1. The only thing missing is the ambiguous constant that we can add to capital function f. We should write the summa of t power n dt equals t power n plus 1 by n plus 1 plus c, where c is a constant that has to be determined by other means. The ambiguous constant is closely related to the ambiguity in choosing the other endpoint of integration that we earlier called a. To see how a determines the ambiguous constant c, let's consider the integral. The summa from a to capital T, ft dt, in the limit where the two limits of integration come together, that is, capital T equals a. In this case, the integral has to be 0. You can use that fact to determine c. In general, the fundamental theorem of calculus is written as the summa from a to b ft dt that equals to ft from a to b that gives us fb minus fa. Another way to express the fundamental theorem is by a single equation. The summa of the differential of the f with terms to dt gives us ft plus c. In other words, integrating a derivative gives back the original function. Up to the usual ambiguous constant, integration and differentiation undo each other. Here are some integral formulas. The summa of c dt is ct and these. Exercise 1. Determine the indefinite integral of each of the following expressions by reversing the process of differentiation and adding a constant. Exercise 2. Use the fundamental theorem of calculus to evaluate each integral from exercise 1 with limits of integration being small t from 0 to t. Exercise 3. Treat the expressions from exercise 1 as expressions for the acceleration of a particle. Integrate them once with respect to time and determine the velocities, and a second time to determine the trajectories. Because we will use t as one of the limits of integration, we will adopt the dummy integration variable t dash. Integrate them from t dash equals to 0 to t dash equals to t. Integration by parts. There are some tricks to doing integrals. One trick is to look them up in a table of integrals. Another is to learn to use Mathematica. But if you're on your own and you don't recognize the integral, the oldest trick in the book is integration by parts. It's just the reverse of using the product rule for differentiation. Recall from lecture 2 that to differentiate a function, which itself is a product of two functions, you use the following rule. The differentiation of fx times gx with respect to dx is equals fx dgx by dx plus gx dfx by dx. Now let's integrate both sides of these equations between limits a and b, which gives us this. The left side of the equation is easy. The integral of the derivative of fg is just the function itself. The left side is fbgv minus fagA, which we often write in the form fxgx from b to a. Now let's subtract one of those integrals on the right side and shift it to the left side. fxgx ba minus integral fx dgx by dx, which gives us a to b summa gx dfx by dx. Suppose we have some integral that we don't recognize, but we notice that the integrand happens to be a product of a function fx and the derivative of another function gx. In other words, after some inspection, we see that the integral has the form of the right side of the equation 4, but we don't know how to do it. Sometimes we are lucky and recognize the integral on the left side of the equation. Let's do an example. Suppose the integral that we want to do is summa from 0 to pi by 2 x cos x dx. That's not in our list of integrals, but notice that cos x equals the differentiation of sin x with respect to x. So the integral is 0 to pi by 2 x d sin x by x dx. Equation 4 tells us that this integral is equal to this, or just pi by 2 sin pi by 2 minus summa 0 to pi by 2 sin x dx. Now it's easy. The integral summa sin x dx is on our list. It's just cos x. I will leave the rest to you. Exercise 4. Finish evaluating summa integration from 0 to pi by 2 x cos x dx. You might wonder how often this trick works. The answer is quite often, but certainly not always. Good luck.